I have actually made the recording on. You sometimes see that no recording is there because I shall not be able to see when I shall be presenting. Then let me know. Then I shall again start recording because finally I shall be sending all these records to you. Okay. So can you see the screen?
Yes,
Yes, sir.
Okay. So we are discussing regarding the synchronous generator, the generator that we use in power stations. Already we have mentioned that around 80% of generators connected in power system are synchronous. Okay. And we are discussing the performance of synchronous generator when it is connected to a large power system. It is connected to a power system. What is the system? A system that may be assumed to be or that may be represented by a single bus. That bus we call the infinite bus. What is that infinite bus? Infinite bus is a bus where the voltage and frequency remain constant, and voltage constant means basically the infinite bus is behaving as a constant voltage source, means it will have zero internal impedance, and constant frequency means it will have infinite inertia. So these are the properties of infinite bus, and with this assumption we are discussing the synchronous generator, how it will be performing. Then we have mentioned regarding different types of synchronous generators, then discuss the phasor diagram of cylindrical rotor type, because cylindrical rotor type machine analysis is a bit simpler. That's why we have, our intention was to start with simple things. Later on we shall be moving towards more difficult things, more complex things. Then from phasor diagram of synchronous machine or synchronous generator, we have moved to develop equivalent circuit. After developing the equivalent circuit, we have derived the power equation. Okay, and how to vary the active and reactive power. The intention to derive power equation was basically how to control the active power generation and reactive power generation of synchronous generator. Why we are attempting to control active, and someone was entering, okay, why we were interested to actually see how frequency active power and reactive power may be controlled, because by actually controlling the active power you can control the frequency, because frequency control depends upon the balance between the active power generation and active power load. Okay. Similarly, reactive power, why we were interested to control reactive power? Because reactive power balance, that means the reactive power generation and reactive power supply, this balance determines the uh, voltage at different buses of the power system. To maintain proper voltage, you must be able to supply reactive power. And from our previous discussion on the previous topic that we were discussing, we know that it is to be supplied locally. That means we have to arrange for the supply of reactive power wherever it is necessary. And obviously, we cannot connect reactive power source at every location of the power system. Where we can connect them, we can connect at location, basically at the substations. Okay, so since they may be controlled from substations, okay, and also from power station, we are discussing how reactive power may be controlled from synchronous generators. That was our intention, to develop active and reactive power equation in case of synchronous generator. Now, let us see what happens or how active power variation may be affected. We have started this discussion. Expression for P is P maximum sine of delta. P maximum, that means EF Vt by Xs. This we have actually written as P maximum when the excitation of the generator is kept constant. Okay. Also, we have seen that it is not feasible or it is not advisable to control the active power generation by controlling the field current of the generator, because field current basically you are supplying some electrical power to the generator through the field winding. That power you cannot utilize to generate electrical power again. Then there is double conversion of electrical power. That is unnecessary step. That's why you should not or we shall not be attempting to control the active power output of generator by controlling the field current. Field current rather we should see that may be controlled for controlling the reactive power. Okay, so we now have arrived at this point where we know that delta, that means the phase angle difference between the terminal voltage and the generated voltage. This is the phase angle difference. This has to be controlled for controlling the active power. And what is this delta? We have, if we go back to the Phasor diagram, then you see that this delta basically is the angle between the terminal voltage and the induced EMF or the internal EMF of the generator. Now, what is the direction of internal EMF generated voltage? This is along the quadrature axis of the rotor. And what is the direction of the terminal voltage? This is basically representing the infinite bias voltage. So its speed or its frequency is constant. The frequency of Vt is synchronous frequency because we have assumed that generator has connected to the infinite bias, and infinite bias maintains constant frequency. So frequency of Vt is constant. Okay, you cannot change it as if, because power system is maintaining that frequency constant, and your generator is really very small compared to the capacity of the total power system. That's why whatever may be the power variation of your generator, it has no capability to control the frequency of the infinite bus, because infinite bus is of infinite capacity. This is our assumption. In practice, that will not happen, but those things we shall be discussing later on. We shall be actually analyzing those things later on. For the time being, we are assuming that synchronous frequency or the frequency of the infinite bus is constant, so frequency of Vt is constant. But what is the frequency of EF? Obviously, this will be determined by the speed of rotation of the rotor of the synchronous generator. Okay, synchronous generator at steady state will rotate at synchronous speed. And what is the synchronous speed? It is a declared frequency is 50 hertz, and depending upon the number of poles of the machine, speed of the rotor of the generator will be decided. So if the generator rotates at that speed, then frequency of EF is also synchronous. So at that case, delta will have a constant value, and during steady state, there will not be any variation in speed. So frequency of EF and frequency of Vt is constant. Okay, but if there is some sudden change in load, or if there is sudden increase or decrease in the input to the generator, then what will happen? The speed of the generator rotor will change. If the speed of the generator rotor will change, then obviously, you can say that the position of the vector EF also will change, because EF is along the quadrature axis of the rotor. That means rotor position determines the delta, or delta is determined by the position of the rotor. Am I clear? Delta is determined by the position of the rotor. If somehow you can increase the speed of the generator momentarily, then what will happen? In that case, that generator rotor will rotate at somewhat higher speed with respect to the synchronous speed. Then, and Vt is rotating at synchronous speed, angular frequency is equal to the synchronous speed, therefore delta will increase. If on the other hand, you reduce the input to the generator, that means the input to the generator through the prime mover, if it is reduced, then what will happen? The generator rotor will rotate at a lower speed with respect to the synchronous speed. Then obviously this is rotating as Vt is rotating at synchronous speed, and EF is now rotating at a speed which is less than synchronous. So as a result, obviously these two phasors will be coming closer, so delta will be decreasing. So this is how, by varying the input to the generator, that means the mechanical power input to the generator through the turbine, you can control the value of delta. That means value of delta may be controlled by controlling the input to the generator, mechanical input to the generator. That means the turbine output of the generator. Turbine output to the generator may be controlled, obviously, by controlling the opening of the steam valve in case of turbo generator, or in case of generators connected in thermal power stations. They are also called turbo generators. Okay. In case of hydroelectric power stations, obviously, water valve, opening of the water valve has to be controlled. So, is it clear? Is it? Could you understand this point, everyone?
Yes, sir.
Okay, this is how
Yes,
delta
yes.
can be varied. Okay, now let us see what happens if we change the value of delta. Now, since we have established the fact that field current will not be varied for varying the output power of the delta, so when we are now discussing regarding the active power variation of synchronous machine, we shall be assuming that field current is constant. Since the field current is constant, obviously P maximum, that means EA VT by XS, that is also constant. So our power angle curve, this is the power angle curve, this curve, sine curve, P maximum sine delta. This is the power angle curve. This power angle curve has a known peak. Okay, peak is fixed. How much is the maximum value of the power? That we know. That is known to us. Okay, so this peak is known to us. So now let us assume that this P0 represents the power output of the generator to the power system. That means the infinite bus is receiving this power from this generator. So at this condition, if we assume that the generator is lossless, that is again a simplification, simplified assumption, but this simplified assumption is needed for us because we want to make the analysis simpler. That's why. So if P0 is the power output of the generator, how much will be the power input to the generator, mechanical power input to the generator? Would you get my
P0.
P0? That means at the steady state, power output from the generator will be equal to the power input to the generator if we assume that there is no loss inside the generator. And for simplicity, we are now assuming that loss to be zero. So input power and output power, they will remain same. So P0 is the power input, P0 also is the power output. So power input line is represented by this straight horizontal line here, horizontal line with respect to the x-axis. Okay, parallel line. And output power, that output point always will be lying on this P delta curve, power angle curve. Okay, so it will be always on this curve, sine curve. Therefore, the intersection between this input power line and power output curve, this is the operating point, P0 is the operating point. Okay, am I clear? Now assume that means, and say it is somewhat delta 0, say. This is the initial operating angle is delta 0. It is not written here, so I assume that this is delta 0. Now, let us assume that suddenly we have increased the power input to the generator by increasing the opening of the steam valve. Say, why I am talking about steam valve? Because our generator is cylindrical rotor type, and cylindrical rotor type generators are installed in thermal power stations. That's why we are talking about the cylindrical rotor type generator. Say, our steam input, steam valve opening is increased a little bit. That's why there is more steam input to the generator, to the turbine. As a result, more mechanical power input is there to the generator. So what happens? This input power line, this line is lifted up. There is a shift from this position to somewhat increased position. Say here. Say this is the this is not drawn here, but I am showing the cursor here. Say this becomes the input power line, position of the input power line. Again, a horizontal line like this. So what should be the operating point? Now this is the power output curve. This is the power input line. Obviously, this will be the operating point. But this operating point will not be achieved at a single step. As soon as I move input power line from here to here, that means as soon as I increase the opening of the steam valve, obviously output power will gradually increase, and a stable operation of the generator will not be achieved immediately. It will take some time. Why it will take some time? Because there will be some change, because delta has to be changed. For change in delta, what is needed? Obviously, momentarily, the speed of the generator has to be changed. And how the speed of the generator will change, you see here. In this is the output power. Okay, this point is the output power P0, and assuming that this is the input power line. So this is the input power, this is the output power. There is difference between input power and output power. So what will happen? Obviously, this additional input given to the generator will cause the generator rotor to speed up. The generator speed will increase. As the generator speed increases, so what will happen? As delta also will increase, because the vector EF and vector data, vector VT, angle between these two is delta. Okay, now EF vector, that is rotating at a speed higher than the synchronous, because rotor is rotating at a speed which is above synchronous. Why? Because we have given more power input, and immediately power output from the generator cannot increase. That's why power input is more than the power output, and as a result, the rotor will increase its speed. Rotor will accelerate. All right. As the rotor accelerates, then what happens? Vector EF will move away from vector VT, because VT is rotating at synchronous speed and EF is rotating at a speed which is somewhat higher than the synchronous speed. So delta increases. As delta increases, you see that operating point will move on this curve. That means accordingly, output power also will increase. Okay, so it means with the increase in delta, output power also will increase. Say somewhere here is the position of the new input power P0. So while delta is increasing, sometimes delta will be meeting at this point where input power line is crossing the output power line. Okay, they will be same, but in this process, can the generator stop at this point? Can the generator operate at steady state condition? That means a synchronous speed at this point at the first attempt. Could you get my question? Could you get my point?
No, sir, at the first attempt.
What is happening? You have increased the opening of the steam valve, means you are giving more power input to the generator. Okay, somewhere here is the line shape. Now output power remains fixed at this point immediately. Why? Because for increasing the output power, delta has to be changed. So the output power cannot immediately follow the input power line. The time lag will be there. Why the time lag will be there? Because for changing the output power, value of delta has to be changed, and for changing the value of delta, this you can say that the speed of the generator has to increase. Otherwise, you cannot change the position of the delta. You cannot change the position of the rotor with respect to the infinite bias voltage. Okay. So speed of the delta will increase because input power is more than output power. Where this additional power will go? It will certainly increase the kinetic energy stored in the generator rotor. That means this energy must go to somebody must absorb this energy. Who is that? Obviously, this is the generator rotor who will be rotating at a higher speed, and as a result, this additional energy input to the generator will be stored in the rotor of the generator. That's why the speed will increase. As the speed is increasing, delta is also increasing because EF vector is rotating at a higher speed with respect to VT vector, so delta is increasing. As delta increases, what happens? Output power also increases. Means difference between the input power and output power decreases. When output power line will be crossing the input power line, output power curve will be crossing the input power curve. There, input power and output power momentarily will remain same, will become same. But what is speed of the generator rotor? It is now above synchronous. That means since the speed of the rotor is above synchronous, it will not be stopping at this point where input power and output power line are input power line and output power curve are meeting at this point, because generator rotor is rotating at a speed higher than the synchronous. So it will continue to rotate at a speed higher than synchronous. That means it will continue to accelerate. Speed of the generator will increase further. As a result, the output power delta will increase and output power will increase further. Means when the output power is increasing further, output power now becomes more than the input power, because output power input power line is fixed and output power curve, this point is changing. So as the delta is increasing, what will happen? Output power line, output power obviously will be greater than the input power. So what will be the effect? Effect will be, since output is now greater than input, generator will now start decelerating. That means it will decelerate from a speed which is above synchronous. From that speed it will start decreasing its speed. But obviously, momentarily it cannot decrease the speed at a single step to synchronous speed. So what will happen? Gradually the speed will decrease, and somewhere here, say after crossing the input power line, say somewhere here, again the input power, again the speed of the rotor and the synchronous speed of the, that means the synchronous frequency of the system, synchronous frequency of the infinite bus, they will become same. Okay, am I clear? That means input power line has been shifted up. As a result, delta is increasing. But after crossing this input power line, delta will continue to increase because speed was above synchronous. Okay, but somewhere say here, let us actually say at this point, what will happen? Since output power is more than the input power, so generator speed was now decreasing from the value it has achieved, which was above synchronous. From the speed it will be decreasing, and maybe somewhere here again the speed will be synchronous. But obviously again the generator cannot run in stable condition at this point, because here the speed of the rotor is synchronous, but in output power is now more than the input power. Is it clear up to this point?
Yes, sir.
Everybody, it is clear? So output power is now greater than input. That means, you see, for stable operation, what is needed? Speed of the generator and the synchronous speed of the infinite bus, they must be same. At the same time, output power and input power, they also must be same. Then only stable operation is possible. Now, what is happening? Output power of the generator is more than the input power, though the speed has become momentarily synchronous. That means this point cannot be the stable operating point. So what happens now? Again, this at this point, output is more than input, so speed will decrease further. Now it will start decreasing below synchronous. As the speed is decreasing below synchronous, what will happen? The distance between the vector EF and vector VT, now it will be now start decreasing. That means now delta will start decreasing from the maximum value it has achieved. Delta have achieved the maximum value, and that is somewhere here. And now, since output is more than input, delta will start decreasing, because now the speed of the generator has started decreasing below synchronous. So at a speed below synchronous, what will happen? Now delta, that means vector EF and vector BT, they will be starting coming closer. Distance between them will be decreasing. That means delta will be decreasing. So when delta is decreasing, output power again is tracing this line in the backward direction. That means initially it was moving in this direction. Now this curve will be traced in the backward direction. So output power will again decrease. As the output power decreases, again somewhere here, the input power line and output power line will be matching together. But now speed of the generator is less than synchronous. So this again cannot be the operating point. So what will happen? The output power line, that means speed of the generator is below synchronous, generator speed will decrease further, will cross this point, below this, it will come here. As a result, again input power line will become greater than the output power. So from here, again the generator will accelerate, again the speed will increase. That means in this way, there will be the to and fro movement of the generator rotor with respect to the infinite bus voltage. That means generator rotor will oscillate. It will oscillate around the synchronous speed. Sometimes the speed will be above synchronous. Again, sometimes speed will be below synchronous. Delta will sometimes increase, reach a maximum value, and then again delta will decrease, reach a lower minimum value, again it will increase. In this way there will be oscillations, and we have assumed that there is no loss in the system. Means we have even not considered frictional loss in the generator. Okay, but there is loss, there are losses, there are winding losses, frictional losses, windage losses, all these things are there. So because of all these reasons, what will happen? You can say the amplitude of oscillation will decrease at each time. That means in the first oscillation there will be a maximum amplitude, then in the second oscillation the amplitude will decrease somewhat, in third oscillation the amplitude will decrease somewhat more. In this way, finally, when the generator becomes stable again, input power line and output power line, they will be meeting at the common point, and speed of the generator and the speed of the infinite bus, they also will be same. That means generator again will rotate at synchronous speed. So at the new steady state with increased power output, okay, generator again will rotate at synchronous speed. Why this has happened? Because we have given a lift, or we have moved the input power, we made it somewhat more than the previous input. So as a result of this, we assume that our the shift was a little. As a result, generator could maintain stable operation even after that increase in input power. Is this discussion clear to you, or you could not understand any point? Let me know so that I can again discuss the same thing or try to explain further.
No, sir,
বলো,
it's clear.
বুঝতে পেরেছো?
Yes.
Okay, now
Yes, sir.
anybody any other question? Now assume that we are attempting this power increase each time by a very small amount, each time by a very small amount. Okay, and we have arrived at this point in the first shift. The second shift, let us increase the value of p input further. So what will happen? In say now this is the input power line, say, okay, somewhere here. So what will happen? From here input power has been shifted to this location, again the speed of generator will increase. Okay, speed of generator will increase, then as a result delta will increase, input power output power will reach this value, say maximum value. Okay, and then again it will be shifted going in this direction. All right, in this way output power will become greater than input. Initially input power was higher, as a result speed of generator had increased. Now as the speed increased, it has increased. Now following the logic we have explained previously, it's in the same logic, generator delta will increase, so output power will increase. Sometime the output power curve, this will cross this point, and since the speed is above synchronous, the generator rotor will be rotating at a speed higher than synchronous. Again this point will be crossed. After crossing this point, what will happen? Output power will be greater than the input power. As a result, generator will be decelerating. People are entering even now. Okay, so as a result generator, okay, will decelerate since the output power is greater than the input power. Okay, in this way somewhere say here after crossing the maximum power point, say after crossing the maximum point somewhere here, say output power output power is greater than input power now, but what may happen now? They say speed was above synchronous, now say speed is below, just equal to synchronous. Now since speed is just equal to synchronous and input power line is just here, say, and say at this point somewhat above this point, say out input power and output, in speed of the infinite bus and speed of the generator has become same. So from here again the speed will be of the rotor will decrease, speed of the generator will start decreasing. As a result delta will decrease from here, and again after some oscillation maybe generator will be stabilizing at this point. Okay, but if you do these things every time, if you change the input power by a very small amount, up to what point you can increase the input power? Up to which point you can increase the input power. That means where will be the input power line, maximum permissible position of the input power line? What will be the location of that?
The P max or delta equals to
Pmax. That means if you increase the value of the input by a very small step, why we are saying that the step will be has to be very small? Because if the step is more, there will be more difference between the input and output power. As a result, there will be larger amplitude of oscillation. Okay, larger amplitude of oscillation. So if we make this change of input power by a very small amount, what will happen? The amplitude of oscillation also will be very small. Now let us assume that we are discussing a theoretical case. Theoretical case because we are assuming that by very small steps somehow we have moved the input power line at this point, at the peak of the power angle curve. Okay, it's just below, it was just below this, now it has been moved here. So if we assume that the input power was, that means the change in the input power was so small that the oscillation that will be created, it will be negligibly small. Then only you can say that maximum permissible power input or maximum permissible position of the input power line will be equal to delta equal to 90 degree, that means peak of the power angle curve. Okay, assuming that there will be no oscillation and very slowly, very slowly we are changing the input power to the generator. So small is the change that because of this change, almost negligible will be the oscillation of the generator rotor. So if we can neglect that oscillation, then only we can say that maximum permissible position of the input power line will be delta equal to 90 degree. And since it is the maximum permissible position, this all will be the permissible position of the output power line also. Okay, that means what you can say? You can say that input power or the maximum permissible power output from the generator is this one. At steady state, this will be the maximum permissible position of the operating point. It cannot go beyond this point because here the output is maximum, and at steady state condition, if the generator can operate at steady state because of the shift in the input power, then this will be the maximum permissible power output point. Okay, what will happen if you make any attempt to increase the output further? Obviously, any attempt, any shift from this point above this point, that means the input power is moved above this point, then what will happen? Always the, if this is the position of the input power line, you see that output power curve is always less than the input power line. That means always the generator will accelerate because input power is always greater than the output power. What happened so long? So long, initially input power was more than the output power, but after that, as delta started increasing, what happened? Output power line sometimes crossed the input power line. Output power curve sometimes crossed the input power line. As a result, output became more than the input power. So here, and that's why the generator could restore it synchronous speed. Generator could restore the stable operation because sometimes input power was more and then again sometimes output power was more. Now, if this is the operating point now, and if you make any attempt to increase the input power further, okay, by increasing the power input line, then what will happen? Obviously, input power line will always be above the output power curve. As a result, generator always will accelerate. There will be no chance of decelerating. For the generator, it cannot decelerate any further. So as it will accelerate always, what will happen? Speed will go on increasing, delta will go on increasing. That means speed never will be able to coming back to its synchronous value. Once it has become above synchronous, it will remain above synchronous always. So it will not be possible for the generator to restore the synchronous speed again. Okay, therefore we can there say that this is the position of the maximum operating point, or you can say that if you draw a vertical line at delta equal to 90 degrees, and left hand side represents the stable operation zone of the power system, and right hand side represents the unstable operating zone of the power system. That means in the steady state, delta will lie between 0 and 90 degree. It cannot cross 90 degree at steady state. Okay, during oscillation, it may cross this point. We shall see this later on also, because when we shall be discussing stability issues, then we shall discuss these issues with further details. Okay, but you see that already we have mentioned that somehow this point has been crossed. Thing is that always you can say that this point was delta synchronous speed achieved has been achieved at some point where that point was above the input power line. If this happens, then obviously this maximum permissible point, that means the 90-degree value, it may be exceeded by the generator rotor, but that is during the dynamic situation, that is during the movement only. But during steady state, the stable value of delta cannot cross 90 degree. It will be at most equal to delta equal to 90 degree. Is it clear or not?
Yes, sir.
বুঝতে পেরেছো everybody? Any question, anybody? If you are having any question, because this point is very, very important in understanding of the whole process of frequency control and active power control and stability. That means the stable operation of our system. That is very, very important to understand this point. So if any one of you are having any doubt, please let me know. I can try to clear your doubts, or even if you could understand, then I can proceed. Any question regarding these things? Anybody? বলো, কারো কোনো প্রশ্ন আছে? If no question, then I can assume that all of you could understand. Okay, that means you see that we could move from here to this point delta equal to 90 degree under what assumption? Under the assumption that generator is having having no power loss at all. This is the assumption, and our generator is a cylindrical rotor generator, so we can say that for cylindrical rotor generator, delta equal to 90 degree is the limit of stable operation, or you can say that this is the limit of so-called steady state stability. These issues, what is steady state stability, we shall be explaining later on. But you see that it is marked here also, starting from this line, that means delta equal to 0 line to delta equal to 90 degree, this line, between these 2 points, the operation of the generator is stable, and when this point is crossed above the delta equal to 90 degree, on the right hand side of delta equal to 90 degree, the operation is unstable. So generator can operate in stable condition if delta is less than equal to 90 degree. Okay, so this, I think it is clear why, how the active power output of the generator may be controlled, and how much you can control, how much we can vary the active power output. That also has been explained here. Now let us come to the reactive power variation. Okay, how reactive power may be varied. Okay, we shall assume that here again, we shall assume that reactive power variation we are examining here under the assumption that active power is kept constant. So we shall assume that there is no variation in the active power output. When this is possible, you are not varying the active power output any further, but varying the reactive power output. When this may be possible? Anybody? বুঝতে পেরেছো? আমি অ্যাক্টিভ পাওয়ার আউটপুটকে চেঞ্জ করতে দেব না, কিন্তু রিঅ্যাক্টিভ পাওয়ার আউটপুটটা চেঞ্জ করব। ওকে, তাহলে অ্যাক্টিভ পাওয়ার আউটপুটটা কনস্ট্যান্ট রাখতে গেলে আমাকে কি করতে হবে বলো? কি করে ভোল্টেজ রিঅ্যাক্টিভ পাওয়ার চেঞ্জ করবো সেটা আমরা পরে দেখছি। বাট স্টিম ইনপুটটা কনস্ট্যান্ট থাকবে, অর্থাৎ স্টিম ভালভের ওপেনিং আমরা কোনো মতেই আর চেঞ্জ করবো না, যা আছে সেটাই থাকবে। ইট উইল নট বি রিডিউসড, ইট উইল নট বি ইনক্রিজড এনি ফার্দার, সো ইট ইজ কনস্ট্যান্ট। দ্যাট মিনস টারবাইন আউটপুট is kept constant. Okay, টারবাইন আউটপুটটা সবসময় কনস্ট্যান্ট থাকবে, জেনারেটর ইনপুটে আর কোনো অ্যাক্টিভ পাওয়ারের ভ্যারিয়েশন হচ্ছে না, সো P remains constant. So by keeping P constant, how the reactive power may be varied, that is the question we shall be trying to find the answer. Okay, Now you see that, let's see the expression, reactive power expression. You see that what is Q? Q is Vt by Xs. Vt is the terminal infinite bus voltage. Again, infinite bus voltage, even if you are varying the reactive power output of the generator, the infinite bus voltage is constant. It is the terminal voltage of the generator as well. But since the generator terminal is tied with the infinite bus, we can say that as the infinite bus voltage is constant, generator terminal voltage is also constant. It will be tied with that voltage. So we cannot change the infinite bus voltage, means we cannot change the terminal voltage. So the terminal is the terminal of our generator. Okay, whatever we can do, whatever we may do, we cannot change the terminal bus, terminal voltage of the generator, since this terminal is connected with the infinite bus, connected with the power system. This is our assumption. Now, with this assumption, Vt is constant, Xs is also constant. So, what is Q? Q is now EF cosine delta, Vt by Xs, EF cosine delta minus Vt. So you see that now delta we shall not attempt to vary, because if you want to control delta directly, then what you have to control? You have to control the active power input to the generator. So this is the method we have followed. So we shall not make any attempt to vary delta directly. Why I am saying directly? That will be apparent later on. But our intention will not be to change the delta. Rather, we shall be focusing on other scope of variation. So what are the other scope of variation? That is EF. That means the induced voltage. Okay. Since you are not changing the value of delta, what is happening? Speed of the generator is not changing. Speed of the generator is not changing means, yeah, how EF now can be varied, because you can change EF only. None other thing is variable here. So if you want to vary EF when the speed of the generator remains fixed, only method is to change the field flux. Okay, because if the flux is increased and the generator rotating, armature is rotating at the same speed, so rate of change of flux linkage will increase. Because of increase in the flux value, rate of change of flux linkage will increase, so more voltage will be induced in the generator armature. Okay, so what you have to do now? You have to change the value of EF. Obviously, you have to change the field flux, means you have to change the field current. So EF now may be controlled by changing the field current. Is it clear? That means you see that the assumption that we have made, that we shall not be changing the value of P, active power variation will not be allowed, means we shall not be attempting to change the delta directly, change the speed of the generator directly. Then generator will be rotating at synchronous speed. So only option therefore is to vary EF. Only option therefore is to change the field flux, and field flux variation is possible by varying the value of field current. So what we shall be doing? We shall be changing the DC field current of the generator. This generator synchronous machine field winding is having DC supply, so DC current of the field has to be changed. Now what happens if the field current is changed? Let us see the phasor diagram that we have drawn here. Okay, now assume that this is the, say this was EF1. EF1 means initially this was the generated voltage vector EF1. Okay, now say this was the terminal voltage. Terminal voltage is constant. So if this is the value of terminal voltage, this is the value of induced voltage. So this will, by neglecting the resistance of the generator, this will be the vector which is IA into excess armature current into synchronous reactance. Okay. Now to make active power output constant, since you are varying EF, that means peak of the power angle curve you cannot change. So it what you can say that, no, not peak, basically the active power output, not peak. We cannot allow the active power to vary. Since we are not allowing active power to vary, so what we shall do? We shall see that this component, the vertical component, basically that means EF sine delta, this, that means this vertical component will not be allowed to vary. Okay, now therefore if you increase the field current, so from say this field corresponding to this field current, say field current has been increased. If field current is increased, keeping the value of EF2 sine delta same as sine delta 2, same as EF1 sine delta. If you increase the value of EF, then what will happen? What will happen? EF2 sine delta remains same as EF1 sine delta, but because of increased current, EF vector has been increased. The value of EF vector is increased. Okay, so what happened? If EF vector is increased, this is the value of delta, EF cosine delta has increased. If even EF cosine delta has increased, you see that Q will be increasing. So by changing the field current from say IF1 to IF2, when IF1 was the field current, EF1 was the induced EMF. When IF2 is the field current, increased field current, IF2 is greater than IF1, EF2 becomes greater than EF1. But what happened? You say now delta 2 has become less than delta 1. Okay, now EF2 cosine delta is greater than EF1 cosine delta. So reactive power output is increased. Okay, now if we decrease the field current, say this was the initial value of the induced EMF. Now we decrease the field current further from this value. By decreasing the field current, obviously field flux has decreased. As a result, induced EMF also will decrease. Since the induced EMF is decreasing, say EF3 becomes the new induced EMF. Okay, and EF3 sine delta is this one. You see that now, since EF3 is less than EF1, to maintain constant active power, that means to make EF sine delta constant, you see that delta 3 has to become more than delta 1. That means as you are decreasing the field current, delta value is increasing. As you are increasing the field current, delta value is decreasing. Now you see that these variation in delta, we have not created this directly. That means this variation of delta is there, but not at the cost of changing speed of the generator. Why this is changing? You go back to the Phasor diagram. Why this is changing? You see that this is changing because of change in the EF. Okay, basically what is happening? Delta is changing. So why this is changing? You see that this is changing because delta is also the angle. Okay, it is the angle between EF and VT. That means EF is due to phi F and VT is due to phi R. So this also is the angle of the angle delta. What will be this angle delta? Obviously, if the field current increases, as a result, what will happen? There it will have another effect on the delta. That means delta variation is possible in two ways, either by changing the field current or by changing the input power to the generator directly. Input power we are not changing. So here the delta is changing because we are changing the field current. As we are changing the field current, there is a change in the armature current. That means there is a change in the armature reaction. As a result, there is a result on delta value also. Okay, so this variation is delta is due to increase or is a variation of field current, as a result of which armature current also increases, or armature current also varies, not increases, because it will depend upon the increase or decrease of field current. Armature current also varies, so delta also is varying. So delta variation is possible in two ways. One is directly by controlling the input power to the generator, which we are not making now. Previously we have done this. Now this variation of delta is due to the variation in the field current. Okay, so you see that here, as a result, if we decrease the field current, delta value increases. If we increase the field current, delta value decreases. Why delta value decreases and increases in this way? Because we have controlled the field current in such a way that means controlling the field current and indirectly controlling the delta in such a way that the perpendicular component of these phasors, F1, F2 or F3, whatever may be, perpendicular component of these phasors is having these all are having the same value. That means EF sine delta is same. Why EF sine delta has to be kept same? Because we want to keep the active power output constant. Okay, EF Vt by excess sine delta. So EF sine delta is kept constant, Vt is constant. So when EF sine delta is kept constant, obviously active power output will also remain constant. So you see that it is possible to change the reactive power output of the generator, keeping the input power constant by varying the value of the field current. We may increase the value of the field current, we may decrease the value of the field current. What will happen if the field current is increased? In that case, reactive power output will increase. And if the field current is decreased, reactive power output will also decrease. Am I clear? Would you understand this?
স্যার ওই ফেজারের
হ্যাঁ,
জায়গাটার একবার বলবেন, ওই আর্মেচার রিয়াকশন যেটা বললেন।
আচ্ছা ওইখান থেকে বেসিক্যালি কি হচ্ছে, আমরা এখানে দেখো হোয়াট উই ওয়ান্ট টু ডু, উই হ্যাভ টু, সিন্স উই our aim is to keep the active power output constant. When we can keep the active power output constant? That can be kept constant if EF sine delta, this component of vector EF, is kept constant. That means the vertical component of the vector EF is kept constant. Okay, so that means if you increase the field current, increasing the field current means field flux is also increasing. So what will happen to the induced EMF? That will increase. So field current is increasing, this component is remaining same, then what will happening? Obviously delta value will be decreasing compared to the previous value of the field current. If you decrease the field current, obviously induced EMF will decrease. But EF sine delta vector is kept constant means now EF sine induced EMF, because of reduction in the field current, you see that delta value will increase. Okay, so now delta is increasing or decreasing because of the variation of EF. Okay, why EF is variation in EF is changing the value of delta? You see that now what happens if delta is varies, if sine is cosine delta, sorry, if delta is increased, what happens? If delta is, sorry, if field current is increased, what happens? Delta value decreases. If delta value decreases, you see that EF increases because EF2 is greater than EF1. EF increases, at the same time delta decreases. Delta decreases means cosine delta value increases. That means EF cosine delta becomes greater than Vt. As a result, Q increases. Q is increasing. So keeping the active power output same, if reactive power output is increased, then what will happen to the armature current? It will increase. Am I clear?
Yes, sir.
You have not allowed the active power output to change, but allowed the reactive power output change, and it has been increased. So that means the active power output remains same, yet reactive power output is increasing. So what is the volt ampere? Volt ampere is increasing. Since volt ampere is increasing, terminal voltage is kept constant. What is happening? Armature current is increasing. Am I clear?
Yes,
So with the increasing the field current, armature current is also increasing. And the armature current is increasing, what will happen? Armature reaction also will increase because phi A will also increase. Am I clear?
yes,
So
sir.
IA is also increasing as a result of increasing IA, and IA is increasing because EF is increasing. EF is increasing because IF is increasing. So when IF is increasing, field current is increasing, and when field current is increased, you see that as a result, armature current also will increase. And it will deliver the same active power, but at a cost of higher armature current. So you are delivering more active power, but sorry, we are delivering same active power, but armature current is more. Am I clear? That means armature current
Yes,
is
sir.
more. As a result, phi is more. Phi is more means armature reaction is also more. Okay. Then what happens? You see that in this phasor diagram, phi f has increased, phi a has also increased. As a result, what is happening? Delta is changing. So delta again is an angle between resultant flux and the field flux. And how the resultant flux and field flux, this angle will be changed. This angle is changing because of changing in phi a also, and phi a has increased in our case. We have seen then armature reaction has been changed because of the effect of the variation of field current. Okay, because as field current is increased, armature reaction is also increased. So delta also will change. How the delta will change? More field current means more armature current, so delta value will become lower. If you reduce the field current, then what will happen? What will happen to armature current if you reduce the field current? Armature current also will be reducing. Okay, previous to the field current is decreasing means armature currents will be reducing, but that means Q is changing. Field current is decreasing means Q is changing. Q changing means what is happening? As Q is changing means active power remains same. Reactive power is changed. So what happened to the power factor of the generator? Power factor of the generator is changing. So in this way, by changing the field current, basically the power factor of the generator will be changing. I shall come to the phasor diagram now later on. Okay, that will make these things more clear. Now only here you now see whether you could understand this by changing the field current of the generator, armature current also will change, and since armature current is changing, armature reaction flux also will change. As a result, there will be a resulting change in the value of delta also. Now, therefore, you see that delta has changed in this case when we have attempted to change the value of field current. But we have not done this by changing the speed of the generator. That's why active power will not change. So delta will change, but active power will not change. Why active power will not change? Because we have not given any additional active power. If no additional active power is given as input, where from this active power will come? Okay, active power cannot change because we have not changed the value of input power. So delta will be changing. But this change is not due to the speed change of the machine. That is due to the change in the armature reaction of the machine. Okay, that is due to the change in the armature reaction. And why armature reaction is changed? Because of the change in the armature current due to the change in the field current. Am I clear?
Yes, sir.
Okay, now you come here. You come here first. Now you see, or no, okay, I think this much is clear that by varying field current, we can vary EF. Either it may be increased compared to the previous value or it may be decreased compared to the previous value. Okay, and as a result, Q will be changing. Okay, now let us see how power factor is changed because of this. Let us go to this vector diagram. Now you see that we have drawn the a smaller part of the phasor diagram here, and instead of drawing all these things here, let us focus on an individual phasor diagram. It will make the things more easy to visualize. That's why. Okay. Now what happened? You see that in this case, you see that EF cosine delta, this is greater than VT. If you this is EF sine delta is constant always, but what happens to EF cosine delta? EF cosine delta, if you take the projection, horizontal projection here, it is greater than VT. If EF cosine delta is greater than VT, what happens to Q? Q will be positive. Okay. If you decrease the field current, sometimes it may so happen that EF cosine delta is 0. Also, if you decrease the field current further, it will be such that EF cosine delta is less than VT. So EF cosine delta, when it is less than VT, what happens then in that case? EF cosine delta minus VT, this becomes negative. So Q becomes negative. If EF cosine delta becomes greater than VT, then Q becomes positive. When EF cosine delta, this becomes just equal to VT, then the difference becomes equal to 0. So reactive power becomes equal to 0. Am I clear? So see, visualize this three phasor diagram here. We have shown this separately here. Here, this is the terminal voltage. This is the induced EMF. This is the angle delta, and this is IA. JIA axis is 90 degree with respect to this vector. Okay. Now in this case, since EF cosine delta is greater than VT, U will be positive. Means we have written the expression for P plus JQ. That means we have measured, if you remember, from the phasor diagram, we have derived the equivalent circuit, and there we have developed the active and reactive power equation. Which active and reactive power? active power delivered by the generator and reactive power also delivered by the generator. That means when the reactive power is delivered by the generator, that reactive power we are saying that is the positive reactive power. So here, when EF cosine delta is greater than Vt, generator will deliver reactive power. Am I clear? Generator will deliver reactive power. The generator always will deliver active power. There is no question about that. But with respect to the reactive power, it will be delivering it if EF cosine delta is greater than Vt. Okay? And in this case, okay, we shall say that generator is overexcited. Why it is overexcited? I shall explain. Now, consider this situation. EF cosine delta is equal to just Vt. EF cosine delta is just equal to Vt. What happens in this case? EF cosine delta minus Vt, this becomes 0, means reactive power becomes 0. That means generator neither delivers nor consumes reactive power. Generator will deliver active power, but it will not either deliver reactive power or consume reactive power. It will be consuming or absorbing no reactive power, simply delivering active power. Means what is the power factor of the generator in this case? Obviously it is operating at unity power factor. Am I clear?
Yes,
Yes,
sir.
yes.
Unity power factor. And if we say that field current is also called excitation of the generator. If the excitation is corresponding to the unity power factor, that excitation, generally we say this is the normal excitation. So if this excitation corresponding to zero reactive power is called normal excitation, obviously field current here is more than that value. That's why it will be called over-excited condition of the generator. Generator is over-excited means generator field current has become greater than the field current corresponding to the normal excitation. Am I clear? বুঝতে পেরেছো?
Yes,
But
sir.
what happens in this case when the excitation is more than the normal excitation? You see that now this is the vector IA axis, JIA axis means this will be the vector IA. And what happens to IA? IA, you see that now it is lagging VT because this is the EF is leading VT, because we know that we have mentioned it previously that power always flows from internal EMF of the generator to the terminal. Means from EF to VT, this is the direction of power flow from leading phasor to lagging phasor. So now, therefore, now you see that IA is lagging VT. IA is lagging VT means the generator power factor is now lagging. Okay. So when the generator power factor is lagging, when it is delivering reactive power. Am I clear? When the generator delivers reactive power, its power factor is said to be lagging. Also, we see that it is lagging because IA is lagging VT. Is it clear? Now, consider this situation when EF cosine delta is less than VT. This is EF and this is EF cosine delta. So it is less than VT. Obviously, Q will be negative. Negative means generator will consume reactive power. If the generator consumes reactive power, it will draw reactive power from what? Who will be supplying reactive power? Supply will, generator is connected to power system. So power system will supply reactive power to the generator. That means from the power system, reactive power will flow into the generator. Generator will consuming. That means with respect to generator, sorry, with respect to the reactive power, generator will be behaving as a load. But with respect to the active power, it is delivering it. It is a generator with respect to active power. With respect to reactive power, it is a load. It is behaving as a load. Okay? Am I clear? So now you see that in this case, this is VT, this is EF, this is the vector JIA axis. So what will be the direction of IA? This will be the direction of IA. Now you see that IA is leading VT. Okay? IA is leading VT. When IA is leading VT, obviously the power factor has to be leading. That means as if the load that is there is appearing as a capacitive load. That's why it is leading. Okay, that means in this case generator is consuming reactive power, means as if the load at the terminal of the generator is capacitive in nature. Or you can say that as if the generator is supplying power to a capacitive load. So now you see that here the generator was delivering reactive power to the load. Who was consuming this? The load was consuming this, the power system was consuming this. So power system was behaving as an inductive load. That's why generator power factor was lagging. That means you see that generator power factor is decided by the nature of the load. Nature of the load is inductive in this case when the generator is delivering reactive power. But when the generator is consuming reactive power, what is the nature of the load? It is capacitive, as if the power system is behaving as a capacitive load. It is drawing active power, but since this is capacitive in nature, it is supplying reactive power and generator is consuming this. So you see that the power factor of the generator is decided by the power factor of the load. Okay, by the nature of the load. When the nature of the load is capacitive, generator is operating as leading power factor. When the power factor of the load is, or the load is inductive in nature, generator is behaving as an inductive, generator is operating as a lagging power factor. And when the load is not consuming or supplying any reactive power, generator is operating at unity power. So is this clear? These three different distinct operation of synchronous generator in the leading power factor, lagging power factor, and unity power factor. And in this case, since the field current is less than the normal field current, because we can have this operating point if the field current is reduced with respect to this operation. With respect to this operation, if the field current is reduced further, then only the induced EMF will be less than this value. So that what will happen? Now the reactive power will be consuming by the generator. That means you see that this condition, since the field current is less than the normal excitation, this is called under excited operation of the generator. Okay, so the overexcited operation means generator field current is more than the field current corresponding to the unity power factor case. Under excitation means field current of the generator is less than the field current corresponding to the normal excitation or unity power factor case. Is it clear? Bolo.
Yes.